In this lesson, we're going to look at a second method of determining the empirical formula of a compound, and it is the method whereby we use a carbon and hydrogen combustion analysis in order to determine the empirical formula of an organic compound. The way that this works is that the organic compound is burned in oxygen, so a sample of it is taken and its mass is determined, and it is combusted by reaction with oxygen. And as you know, when a hydrocarbon is combusted, it produces carbon dioxide and water. So the gases that are produced from the reaction pass through this tube, and the water that's among those gases will be absorbed by a water absorber. So that would be some kind of an anhydrous salt that absorbs water. The carbon dioxide would continue on and be absorbed in the carbon dioxide absorber. By measuring the masses of these tubes before and after the experiment, we can determine the mass of water and the mass of carbon dioxide that's been produced through the combustion of our unknown sample. This data, the masses of the water and the carbon dioxide, can then be used to help us work towards finding the formula of the empirical formula. Let's look at an example to see how we solve this type of a problem. In this example, a 1 gram sample of pure compound containing carbon and hydrogen was combusted in a carbon-hydrogen combustion analyzer. The combustion produced 0.6919 grams of water and 3.338 grams of carbon dioxide. What is the empirical formula of the compound? So as you'll notice, the data that is collected in these experiments is quite precise, and that is required in order to obtain results that are expected in terms of the empirical formula being a very nice whole number ratio. So if we look at what's happened here, we started with a compound that has some amount of carbon in it and some amount of hydrogen. And we're reacting it with oxygen, and we just have excess oxygen available. So we're not concerned about the amount or the quantity of oxygen that has been reacted. Okay, and this combustion reaction will produce H2O and CO2, and we know that the mass of the CO2 that was produced was 3.338 grams, and the mass of the water that was produced was 0.6919 grams. Now what's important to note here is that all of the carbon in the original hydrocarbon has been converted into the carbon dioxide. So essentially all that carbon is now trapped in the carbon dioxide. And for the hydrogen, all of the hydrogen from the original sample is now part of the water in the sample. So we can use this information to help us work backwards to figure out the amount of carbon and hydrogen in the original sample. As you'll recall from the questions that we've done before, we can set up a little chart to organize our information when studying empirical formulas. So the headings that we'll need here, in this one we're not going to need the mass, we're going to need the moles and the ratio. Okay, so we need information about carbon and about hydrogen. Now what's going to help us here is not the mass of the carbon dioxide in the water, but the moles, because if we are working with moles, then we're working with the actual number of carbon molecules. So we can find the moles of carbon dioxide by dividing by the molar mass. The molar mass of carbon dioxide is 44.01. So if we take that molar mass, we can use it to find the moles of carbon dioxide, which are 0.075846. Now this is the moles of the carbon dioxide. So sometimes what I do is I actually put a little subscript, so this is the moles of carbon dioxide. What I need for my empirical formula is the moles of carbon. All of the moles of carbon that were in the original sample are now in the carbon dioxide. If I know the moles of carbon dioxide, I also know the moles of the carbon that I have in this sample, because for every 1 mole of carbon dioxide, there is 1 mole of carbon. So the moles here is equal. Okay, so therefore, for my empirical formula chart, I know the moles of carbon in this 1 gram sample. Let's do a similar analysis for water to determine the hydrogen. I can figure out the moles of water, and I do that by dividing by the molar mass of water, which is 18.02, and I get a moles of 0.38396. Now in this case, to determine the moles of hydrogen, I need to take into account the ratio. For every 1 mole of water, there are actually 2 moles of hydrogen. So my number of moles of hydrogen that was in my original sample is whatever the moles of water I have are times 2. Okay, so my moles of hydrogen in this sample are 0.076792. So from this data, we have been able to determine the mole ratio between carbon and hydrogen. And as you know, in an empirical formula, the proper form of the ratio is a whole number ratio. So I need to convert this to a whole number ratio by dividing by the smallest of the 2 amounts of moles. Okay, and so in this case, I'm going to divide both of them by 0.075896, okay, and I get a ratio of 1 to 1. Okay, so therefore, my empirical formula in this case is CH. Now we'll do a second example, and this example is slightly different because the organic compound that we're studying contains oxygen as well. So we've got the size of the sample. We've got a 0.684 gram sample of oxygen. And using the combustion chamber, we're able to determine the amount of carbon dioxide and water that's produced. So the amount of carbon dioxide in this case is 1.312 grams, and the amount of water that was produced in this reaction is 0.805 grams. The initial sample that I burned was 0.684. I'm going to build my chart down here, and in this case, when we're dealing with oxygen as well, we are going to need our mass column, and you'll see why a little bit later. It'll help to organize our information. Okay, so we've got carbon, we've got hydrogen, and we've got oxygen in our sample. So much like in the last example, we're able to use the carbon dioxide to determine the number of moles of carbon in the sample, and we're able to use the hydrogen to determine the number of moles of hydrogen in the sample. Okay, so we do that by dividing by their individual molar masses. So when I've got 0.29811 moles of carbon dioxide, that translates into the same number of moles of carbon. For the water, by dividing by 18.02, I find that I have 0.044673 moles of water. Okay. The moles of hydrogen is going to be double that, however, okay, because of the formula of water and the ratio of hydrogen to the water molecules. Now, to find the amount of oxygen that's in the sample, we're going to use the information that we have about the total mass of the sample. Since I've been able to determine the moles of carbon and the moles of hydrogen, I can work backwards here and figure out what mass of carbon is in that sample. So I'm going to be able to times by the molar mass of the elements to determine the mass of the carbon and the mass of the hydrogen. And so what I find here is that I have 0.35803 grams of carbon and 0.090238 grams of hydrogen. So again, with these questions, I've talked about it before, it's really important to carry lots of significant digits. You're given very precise data in the question, and our ultimate goal is to get very nice whole number ratios. And so in order to do that, you need to carry lots of significant digits. Now that we have the mass of the carbon and the hydrogen in the original sample, we can use that information to find the mass of the oxygen, because the 0.684 grams is going to be equal to the mass of the carbon plus the mass of the hydrogen plus the mass of the oxygen. So by taking the 0.684 and subtracting the mass of the carbon and the mass of the hydrogen, we are left with a mass of 0.23573 grams of oxygen, which I can then use to determine its moles by dividing by 16, which is the molar mass of oxygen, and that is the moles of oxygen. My next step is to then determine the whole number ratio by dividing all of the values by the smallest, which is the 0.0147332, and I find that I get 2.02 and 6.06 to 1. So this I can round confidently to 2, and this I can round confidently to 6. If you're not getting nice whole number ratios at this point, there's a very large possibility that you have made some kind of an error along the way. And with all the small calculations that you're doing, it is quite possible for that to happen. Okay, so you need to be checking and be making sure that you're getting whole number ratios, or work backwards to find the error that you've made. Now, it is possible to do similar type experiments with different elements. So you'll see in the extra practice that you're doing that you'll encounter compounds that will have nitrogen in them, for example, or ones that will have chlorine. And you're going to use the same concept of working with the products to determine the moles of the reactants and thus the elements.